Hello everyone and welcome again to this revision series of physics lectures, revision of class 11th physics. Today we are going to start the next section of this series, which is the chapter of center of mass or system of particles, including collisions and conservation of linear momentum, etc. So let us begin. So the first aspect we understand in this is about center of mass for a system of particles. So as we know, the center of mass, or what we call COM, it is the symmetry point about which the mass of our system is symmetrically distributed. So for example, if we have a discrete particle system, that means individual particles or individual lumps of mass, for a discrete particle system where our particles are distributed in three-dimensional space in general with respect to an rectangular coordinate frame, let's say, if our particles are distributed like this in a certain region, so M1 is at position X1, Y1, Z1, M2 is at position X2, Y2, Z2, and so on and so forth. Okay. Then the center of mass of this system will be somewhere such that the mass of the entire system is symmetrically distributed with respect to the position of the center of mass. So if this is our entire system having mass, then the mass should be symmetrically distributed with respect to that. So the position of the center of mass is given by this relation. It becomes summation of mass into position for all the particles divided by summation of mass or total mass. So as you can see, it becomes like a statistical weighted mean kind of formula, where the weighting is done with respect to the, or the weighing is done with respect to the mass. Okay. Or we can reduce this to individual coordinates, that x coordinate of the center of mass is summation mx divided by summation m. The y coordinate of the center of mass is summation my divided by summation m. And the z coordinate of the center of mass is, okay, where the summation is done in each case from 1 to n for the n number of particles. So this becomes the definition of center of mass for a discrete particle system. Okay. Whereas when we consider a continuous mass distribution, so we have something like a rigid body, let's say, where the total mass is m, and it's in, we want to find the position of the center of mass with respect to our rectangular coordinate system, let's say again. So what we do is we divide this mass into differential particles whose individual positions are like this. Okay. So the center of mass's position will be such that the position vector of the center of mass will be integration of RdM divided by integration dm. So it is basically a summation of R into delta M divided by summation of delta M. But now we are making delta M tend to 0, so it becomes an integration. So for very small delta M, if we apply the limit that delta M is tending to 0, then it becomes this integration. Of course, integration of dm is the total mass M. So this becomes the integration formula for position of center of mass for a continuous mass distribution. And as you can see here, that we can also write this in terms of individual coordinates. Okay, so let's start with some examples of the applications of these formulae for center of mass and position of center of mass. And through these applications, we'll learn various techniques also, which can be used, techniques and shortcuts, etc. So let's start with an example like this. Suppose we have a structure that is made like this. So a triangular frame kind of thing which is made, but of different materials. Okay. So let's say that this is a length of 30 centimeters. This is a length of 40 centimeters. Now, so the triangular frame is made of thin rods of uniform cross-sectional area. Now, for rods AB and AC, the density of the material is rho naught, but for the rod BC, the density is equal to 2 rho naught. So this is heavier. In terms of mass per unit volume also it's heavier. The density of this rod BC is more. Okay. So we have to find the position of the frame's center of mass. Okay. With respect to the corner point A. With respect to this corner point A, you have to find the position of the center of mass. So let's understand this as a problem. So I'll just give you a minute to go through this and we'll discuss how to solve. Okay, so the main concept we'll use in this problem is that we can replace each of the rods with equivalent particles located at the center of mass of that particular rod. So what we can see here is that the rod AB has its center of mass at the midpoint, say C1. The rod AC has its center of mass at the point C2, and the rod BC has its center of mass at the point C3. So this will be 15 centimeters. This will be 20 centimeters. Okay. This angle will be 53 degrees, and this will be 25 centimeters. That's the geometry part over here. Now we can see that the rod AB can be replaced as a point mass, let's say M1 at the point C1. So this M1 will be density into some area of cross section into 30 centimeters. Okay. And the position of C1 will be at 0, 15. 15, 0 in coordinates. Okay. Similarly, the rod AC, it can be replaced by a mass M2 at C2, where M2 will be equal to the same density into area, but into 40 centimeters. Okay. And C2 will have a position of 0, 20 centimeters. Okay. And likewise, the rod BC can be replaced at some mass M3 at the position C3. Now M3 will become 2 times rho naught into the same area, but into 50 centimeters. Okay. And C3 will come to, but now notice first of all that M1 is to M2 is to M3 will become 3 is to 4 is to 10. Okay. So if we can take M1 as 3M, M2 as 4M, and M3 as 10M, like this, where M is basically going to be equal to rho naught into area into 10 centimeters. Small a is the area of cross section of each of the rods. Now let's come to C3's position. So C3's position, as you can see, will be like this, that if we take this point as our origin, A as our origin, then C3 is the midpoint of AB, of BC. So this is 30, 0, and this is 0, 40. So C3 is the midpoint. So it will be 15, 20 centimeters. Okay. So now our system becomes a system of 3 particles. It becomes, instead of something so complicated, it just becomes a system of 3 particles which are located like this with respect to our reference frame, where the corner A is our origin. Okay. So we have M1 at the point C1, which was 15, 0. We have M2, which is at the point C2, which was 0, 20. And we have M3, which was at the point C3, which was 15, 20. Those are the coordinates. So the center of mass of the system will be somewhere here, which is at some coordinate xc and yc, let's say. Okay. So xc will be summation mx divided by summation m. So that is m1 into 15 plus m2 into 0 plus m3 into 15 divided by m1 plus m2 plus m3. Okay. Now we have seen that m1 is to m2 is to m3 was 3 is to 4 is to 10. So we took m1 as 3m, m2 as 4m, and m3 as 10m. So the x coordinate of the center of mass will become 3m into 15 plus 0 plus 10m into 15 divided by 3m plus 4m plus 10m. So as you can see, it's becoming 3 plus 10, 13m into 15 divided by 3 plus 4 plus 10, that's 17m. So it's becoming 13 into 15 by 17 centimeters. This is the x coordinate of the center of mass, which will become 11.47 centimeters approximately. Okay. And similarly, we'll find the y coordinate as summation m into y divided by the total mass. So that will become m1 y1 plus m2 y2 plus m3 y3 divided by summation m. So this time that will become 0 plus m2, which was 4m, plus m3, which is 10m divided by summation 17m. So this becomes a y coordinate. Okay. So from this we can see that the center of mass is at the position in centimeters like this. So this is one of the important concepts over here. Okay. Now let's move on to some integration based examples. So next up we'll see that if we have a material which is of variable density, or what we call an anisotropic material. So let's say what we are having is say we have a cylinder which has a uniform cross section. However, the cylinder is made of anisotropic material. The density of the cylinder varies with position, let's say. So within the cylinder, if we take a point which is at a distance x with respect to this end of our cylinder. So this is a solid cylinder of length L and radius R, but it is made of what we call anisotropic material. That means it is non-uniform in physical properties of variable density, such that density rho varies with the x coordinate. According to this formula. Okay, where rho naught is a constant and L is obviously the length of the cylinder. So now we have to find the position of the center of mass. We have to find the position of the center of mass in terms of the x coordinate of the center of mass with respect to the origin, which is the center of the left face of the cylinder. This left hand side face is a circular face, or it looks like a disc shaped face. So we have to find the position of the center of mass as the x coordinate with respect to that. So just go through this for a minute and we will discuss how to apply the integration concept over here. नहीं होगा. Okay, so let's understand this example. So obviously what we'll do here is, because the density is varying with the x coordinate or the x axis only, so we will slice this into discs. Okay, we'll slice it into thin discs, which are such that the surface of each disc or the plane of each disc is parallel to the YZ plane. So the entire disc will have a uniform density. Okay, so this is our y-axis, this is our z-axis. So at a distance x like this, if we slice a thin disc like this of thickness dx, then the mass of this disc will become the density into the volume of the disc, which will become density into pi r square into the thickness. Okay. So now the position of the center of mass of this system, let's say it's somewhere over here. So the x coordinate of the center of mass will come from this formula, integration of x dm divided by the total mass, or integration of x dm divided by integration of dm. So here dm is equal to this one, because we know here that density is varying with position according to this formula. It is given to us. So the x coordinate of the center of mass becomes integration of x into rho dv divided by integration of rho dv. So further that becomes integrated from x equal to 0 to x equal to L. So as you can see, this becomes x square by 2 plus x to the power 4 by 4 L square divided by x plus x cube by 3 L square for the same limits. So this will become 1 by 2 plus 1 by 4 L square divided by 1 plus 1 by 3 L. So 3 by 4 L divided by 4 by 3. So this becomes the x coordinate of the center of mass. So I'll just leave you to go through this for a moment, then we'll move on to the next question. Okay, next let's move on to some of the standard derivations. For example, center of mass of a thin semicircular shaped arc. Okay, so suppose what we've done is we have a thin rod which is having uniform cross sectional area, but that is bent into the shape of a semi arc, like this here. So this is a thin uniform cross section and isotropic. So isotropic will mean it has a uniform density. Okay, semicircular arc with the center of curvature being the origin. Okay, and radius r. So we have to find the location of the center of mass. So obviously the center of mass will lie somewhere on the y-axis, because the y-axis is an axis of symmetry. So the center of mass will be at the position on the y-axis, okay, having a y coordinate such that now that y coordinate we will calculate by the integration method. And as I'm sure most of you are aware how to do this integration, always on a circular arc or semicircular arc or basically that kind of shape, we take the position of a particle in terms of its angular position, theta, and we always slice a differential length such that it becomes a differential arc. So it subtends a small angle d theta. So as you can see that for that particle, so for the differential section dl, dl is equal to r d theta, and the mass of that element is linear mass density into L, into dl. So linear mass density will become total mass upon pi r. Okay. So this thin uniform, this thing, it has a radius r and a mass m. So m divided by pi r is the linear mass density or lambda, and dl is r d theta. So the mass of that small length element becomes m upon pi d theta. Okay. Now we can see that the position of that is such that its y coordinate for that element is nothing but this vertical height here, that's the y coordinate. So that you can see is r sine theta. So now these two will be substituted in the integral over here, this integral. Now for the limits of integration, remember we'll be integrating for the entire mass from this end, let's say A, to this end B. So the value of the angle theta at the end A will be theta equal to 0. At the end B, theta will be equal to pi or 180 degrees. So we're left with this integration. So we get this final value, which is 2r by pi. So this is the y coordinate of the center of mass with respect to the origin, which we have taken as the center of curvature of the semicircular arc. Okay, and y-axis as the axis of symmetry. So this is a standard derivation and one of the standard formulae that you should be aware of. For example, an adaptation of this derivation is the case of a general circular arc, which is not necessarily subtending an angle of 180 degrees, but could be subtending any general kind of angle. Let's say we have a semi arc like this. We have an arc like this, which is subtending some general type of angle, let's say, at the position of its center of curvature. It might be somewhere here. This whole angle is, let's say, alpha. The radius is r. So by a similar derivation, it's possible to show that the center of mass lies on the symmetry axis, which will be the angular bisector. So this bisects this angle, these two. So this is the symmetry axis. So if we take this as our x-axis, then the center of mass will be somewhere here. Where the x coordinate of the center of mass, or the distance from O to the center of mass, will be given by this formula. Okay. So this is again a standard formula which you can derive by the same kind of method that we've done earlier. But more importantly, you can just conveniently remember this formula as r sine alpha by 2 divided by alpha by 2, where r is the radius and alpha is the angle subtended by the arc at the center of curvature. Okay. Now likewise, another of the standard derivations is the case of the the thin uniform disk, or rather semi-disk. So this is a thin uniform semi-disk of mass m, radius r. So once again you will see that here the axis that bisects the 180-degree angle at the center of curvature of the disk, that is our axis of symmetry. So y-axis is our symmetry axis. And the center of mass will lie on the y-axis. Okay. Now this YCM we will again calculate by integration ydm divided by total mass. But this time when we are doing the integration, we will slice this semi-disk into semi-rings, because we already done the derivation for the semi-ring. Okay. And if we take a semi-ring of radius r and thickness dr, we can see dm is the semi-ring, a thin semi-ring. So it has mass per unit area into dA. So mass per unit area sigma is m upon pi r square by 2. And the area of the ring will become pi r, that is the length, into the thickness. So dm, which is sigma dA, becomes 2m upon r square into r dr. And the y coordinate of this mass is, this mass dm center of mass is 2r by pi. So by completing this substitution, by substituting these here, we will see that we'll get the y coordinate of the center of mass as 4r by 3 pi. So again, this is a standard formula that you should remember. Center of mass of a semi-disk. And like this, some of the other standard formulae to know is that center of mass for a solid hemisphere, a solid cone, a hollow hemispherical shell, and a hollow conical shell. So all these are the standard formulae that you should know, in addition to semi-ring, semi-disk, etc. that we have discussed. Okay, so let's look at one more of the standard derivations. We will look at the case of the hollow hemispherical shell. So again, let's take our origin of our coordinate system at the center of curvature of the hemispherical shell, and the y-axis as the axis of symmetry. So you can see the mass distribution is on the surface like this. So this time we will slice it into thin rings. So we'll take our differential element as a ring like this, which is of a thickness, let's say ds, and of a radius small r. So this is a thin shell which has mass capital M and radius of curvature capital R. So this radius here is capital R. So if we've taken our differential ring at an angular position theta like this, then we can see that thickness of the ring dr will subtend a small angle d theta. So the thickness will become r d theta. Okay. So the mass of that ring will become again sigma into area. So the area will be circumference into thickness. Now you can see here that the radius of that particular ring will become r cos theta, and the thickness we've already seen is r d theta. So the area becomes 2 pi capital R square cos theta d theta. This becomes the area. Okay. So the mass becomes sigma, which is m upon 2 pi r square, because sigma will be mass upon surface area. That is total mass upon surface area of hemisphere, which is 2 pi r square, into area, which is 2 pi r square cos theta d theta. So you can see that the mass of that differential ring will simply become m into cos theta d theta. And the y coordinate of its center of mass is over here. You can see this is the y coordinate. So that is r sine theta. So the system's y coordinate of center of mass will be integration y dm divided by total mass. So that's integration of r sine theta into dm, which is m cos theta d theta, from theta equal to 0, theta equal to pi by 2 divided by the total mass. So you can see we'll get the y coordinate of the center of mass as r by 2. So this is the standard derivation for the center of mass of a hollow hemispherical shell. So I'll just leave you with a minute to go through this derivation, then we'll move on to some more concepts related to center of mass next. Okay, so next up we will move into the next set of concepts, which is to do with motion of center of mass. For a given system of particles. So the idea is here that if we have a system of particles, let's say we are initially talking about discrete particles, which are moving about. So maybe that some of them are moving and some of them are not moving, or all of them are moving, it doesn't really matter. But as long as at least one of them is moving, the center of mass will also be moving. So the center of mass will also be in a state of motion. So how to calculate? So we start with the understanding of displacement of the center of mass. Now obviously displacement is defined as change in the position vector. Okay. And the position vector of the center of mass itself was defined as summation of m into r divided by summation m. So now because the masses of our particles are remaining constant, we can see that this further becomes summation of m into change in position divided by summation of m. So it becomes summation of m into displacement divided by summation m. So the formula that we get for displacement is summation m into s for individual particles divided by summation m for the whole system. Okay. And similarly, we can define velocity of the center of mass as the instantaneous rate of change of position. So this is a kinematics definition. So this will become instantaneous rate of change of summation mr divided by summation m. So by very similar method, the rate of change will now apply directly to the position vector of each particle inside the summation divided by the total mass. So we have a symmetrical formula for the velocity of center of mass. Becomes summation mv divided by summation m. And similarly, we'll have acceleration by exactly the same process, the instantaneous rate of change of velocity, and then substituting this and all this. So we will get acceleration of center of mass is summation m into a divided by total mass. Okay, so let us see an example related to this. So for instance, if we have this kind of situation, we have a smooth surface on which there is a wooden plank placed. And on the plank at one end, there is a man. So the wooden plank has mass, say, 20 kilograms and length 12 meters. And the man has a mass of, let's say, 60 kilograms. Okay. Now, if the man walks to the other end of the plank, you have to find the displacement of the plank itself. Okay. So just leave you with a minute to go through this question and we'll discuss the solution. Okay, so let's understand this question. So first of all, see what is happening here is because the surface is frictionless, the center of mass will not move. So what we have to understand is that, okay, because the surface is smooth, so when the person is moving forward, he will apply a backward frictional force on the plank, and the plank will apply a forward frictional force on him. So as a result of that, what will happen is that as he moves forward, the plank will move backwards. So he would have made a displacement like this, let's say S1, and the plank would have made a displacement like this, let's say S2. But the displacement of the center of mass will be zero because the floor below is smooth. So the net force on the system is zero. Okay. So keeping that in mind, the way to solve this problem will be that we'll understand that in the beginning, this is a mass of 60 kg, which is located here, and the plank's center of mass is here. So there's a mass of 20 kgs, which is located at the center of the plank. So it is at a distance of 6 meters from here. The length of the plank was 12 meters. The mass of the plank was 20 kg. Okay. So the system center of mass is somewhere over here. This is the center of mass of the system. Okay. So by the time the person walks to the other end of the plank, this is what should happen. The system should remain where it is. The system center of mass should remain where it is. But individually, the person and the plank system becomes like this. Okay. So let's say the plank displaces by S2 backwards, whereas the person displaces by S1 forwards. Okay. But displacement of center of mass should be zero. So displacement of center of mass, remember, is summation m into s divided by summation m. We are writing for a one-dimensional system, so this will just become m1 s1 plus m2 s2 divided by m1 plus m2 should be equal to 0. So we'll get this relation that 60 kgs multiplied by s1, okay, plus 20 kgs. But now when I'm writing in 1D, I will write this as a minus s2 should be equal to 0. So this displacement of the person is this vector here. So I have 3s1 is equal to s2 is the first relation. Okay. Now from the diagram, you can see that the relative displacement of the person with respect to the plank is the total length. So displacement of person 1 with respect to the plank is given by this relative displacement equation. Okay, so this will convert to L is equal to S1 plus S2. Because when we do the vector difference, it is the opposite, okay, direction. So S1 minus S2 will become magnitude of S1 plus magnitude of S2. That is equal to the length of the plank. That is this. Okay. So now solving these two equations, we will get the final relation that the displacement of the plank, which is what we are looking for, S2, okay, will be 9 meters. So become our answer. whereas the displacement of the man will be 3 meters in this direction, whereas the displacement of the plank will be in this direction. So this becomes the conclusion of this question. So with this, we finish today's session, and next time onwards, we will look at linear momentum and conservation of linear momentum, and velocity of center of mass, then eventually impulse momentum theorem for a system of particles, and from that we will move on to collisions, etc. So that's it for today's session, people. Wish you all the best, and thank you for attending.